Ever feel like time is just running away from you? Like you never have enough of it, always racing the clock, trying to cram everything in. It feels so real, doesn't it? This constant forward march, this undeniable ticking that seems to govern our whole existence.
Yeah.
But what is that feeling, that deep-seated sense that time is this fundamental universal thing that just passes? What if that's completely wrong? What if time, as we, intuitively understand it, doesn't actually exist in the way we think it does?
That sounds almost, well, absurd at first, right? Because our entire lives are built around time. But the expert we're drawing from for this deep dive uses a really great analogy. Think about the idea that the Earth is flat.
Okay.
On our everyday scale, walking around, even flying relatively short distances, the flat Earth idea, it seems to work perfectly fine. Our intuition says, yep, it's flat.
Mm-hmm.
But modern physics, when you look at the universe on a much larger scale or at high speeds or with extreme precision, well, it tells us our intuition is just based on a limited perspective, and time works the same way.
Exactly. And that's the core idea we're diving into today. We've been spending time with a fascinating source. It's a conversation with an astrophysicist who makes a really compelling case for why time doesn't exist as this universal backdrop, at least, not according to the physics that governs everything.
Yeah.
So our mission here is to take you, the listener, through that fascinating conversation, unpack the evidence, wrestle with the mind-bending implications, and show you why this isn't just some abstract theoretical physics idea, but something that has real, tangible consequences we actually use every single day. So let's jump in by looking at that intuitive feeling we all have. We use clocks, we make appointments, we say things are happening at the same time across the world. It just feels like there's this universal clock ticking for everyone, everywhere.
And that feeling is totally understandable because, well, it works for the vast majority of our experience. If you're walking across Paris or even flying from one city to another, the curvature of the Earth is pretty negligible, right? You can treat it as flat for practical purposes. It's the same with time. In our daily lives, moving at relatively slow speeds compared to light and experiencing gravity as we do on Earth's surface, the effects that physics says should mess with our sense of universal time are just so incredibly small. Our everyday clock simply can't detect them. The expert in our source really emphasizes this point. Your watch, your phone clock, they're just not precise enough. We're talking about differences that only become apparent at, like, orders of precision, like billionths of a billionth of a second.
Wow.
Which is a level of accuracy only achievable with, cutting-edge scientific instruments today.
Billionths of a billionth. Okay, so if our everyday experience and clocks are essentially blind to these effects, how does science actually demonstrate that universal time isn't a thing? What's the concrete evidence?
Yeah. This is where those incredibly precise instruments come in, atomic clocks. The source talks about just how accurate these are. They're capable of being off by less than a single second over the entire 13 billion year age of the universe.
That's staggering precision.
It really is something we couldn't even dream of until relatively recently. And the key experiments involve taking two of these perfect clocks, synchronizing them absolutely precisely, and then, well, doing something really simple. The expert describes experiments where one atomic clock is simply moved one floor up in a building, left there for a while, and then brought back down.
Just one floor.
Just one floor. And what happens? They are no longer in sync. The clock that was moved, even just a few meters vertically, recorded a different passage of something.
So wait, if these clocks are supposed to be perfect, and they measure the exact same thing, this universal time, but they show different readings just because one was moved up one floor, that really challenges the idea of a single universal time, doesn't it? I mean, whose clock is right?
That's the crucial point the source makes. The conclusion isn't that one clock is wrong and the other is right.
Yeah.
The conclusion is that they aren't measuring a single universal time, because such a thing doesn't exist. What they are measuring is duration.
Duration.
Yeah. They're measuring the length of their own history, their own journey through what physics calls space-time. Each clock measures the duration it experienced along its specific path and under its specific conditions.
Duration, not universal time.
Oh, okay.
So it's not just a theoretical difference, then it's something you can actually measure.
Yeah.
And you mentioned this isn't just lab science. This has real-world applications.
Oh, absolutely. This isn't just some abstract idea floating around in physics departments. The fact that universal time doesn't exist as a fixed backdrop is actually fundamental to technologies we rely on every single day.
Like what?
Well, the prime example is GPS.
Ah, right, GPS.
The satellites orbiting Earth are moving really fast relative to us on the ground, and they're also in a weaker gravitational field than we are down here. Both of these factors, according to Einstein's theories of relativity, affect the rate at which clocks tick, or, maybe more accurately, the duration measured by the atomic clocks on those satellites compared to clocks on Earth.
Okay, so speed and gravity both play a role.
Exactly. And if GPS systems didn't constantly calculate and correct for these precise differences in duration, if they just assumed time was universal and all clocks ticked at the same rate everywhere, their position calculations would be wildly inaccurate. The source cites an error of about 22 kilometers per day.
22 kilometers, that makes it totally useless.
Completely useless. GPS only works because it precisely accounts for the fact that duration passes differently depending on speed and gravity. It relies on universal time not existing.
That's incredible. Are there other examples?
Yeah, it's being used in other fascinating ways too. Altimetry, for instance. Measuring altitude very precisely. Even the tiny difference in gravity, just a few centimeters or meters higher off the ground, causes a measurable difference in the duration recorded by an atomic clock compared to one at ground level.
Seriously, centimeters?
Yep. Atomic clocks can now be used as incredibly precise altimeters just by detecting this desynchronization caused by the change in the gravitational field at different altitudes.
Wow.
And they're even exploring using it in resource prospecting.
Like looking for oil or water.
Exactly. Differences in underground density, maybe indicating water, oil, or minerals, slightly alter the local gravitational field above them. Atomic clocks, being sensitive to these minute changes in gravity via the way they affect measured duration, can potentially help map these underground structures.
So these essential modern technologies and even new exploration methods, they literally rely on the fact that universal time doesn't exist. That's
Right.
wild. So how did physicists move from that initial observation, like the atomic clock experiments, to this radical new understanding of reality? Where did space-time come from?
Well, that journey really takes us back to Einstein. He didn't just wake up one day and decide time wasn't real. He was wrestling with experimental results and thought experiments that simply didn't fit with the old Newtonian idea of absolute space and absolute time.
Right. Newton's universe was like a fixed stage.
Kind of, yeah. And the source brings up Einstein's thinking about trying to synchronize clocks. Imagine trying to make sure a clock in Paris and a clock in Berlin showed exactly the same time simultaneously.
Okay, how would you do that? Send a signal.
Right. But Einstein realized the core problem. Any signal you send, even light, the fastest thing there is, takes duration to travel. So by the time the signal from Paris reaches Berlin, duration has passed. There's actually no way to verify absolute universal simultaneity, this idea that something is happening exactly now, everywhere in the universe at once.
So now isn't universal.
It isn't. What is simultaneous for you depends on your motion relative to the events you're observing. And this tied into perplexing results that were already around, like the Michelson-Morley experiment from the mid-1800s. That showed that the speed of light is constant, no matter how fast the observer is moving.
Which didn't make sense under Newton's law.
Made no sense at all in a universe with absolute time and space. It puzzled physicists for decades.
Right, so the universe was kind of dropping these hints. Strange experimental results, the constant speed of light. But it took Einstein's genius, thinking about something seemingly simple like synchronizing clocks, to connect those dots and realize the fundamental assumption about time itself had to be wrong.
Precisely. He saw that if universal simultaneity doesn't exist, then universal time as a fixed, absolute flow couldn't exist either. It just wasn't compatible. He needed a completely new framework, one where space and time aren't separate stages where events happen but are somehow interwoven.
And that's where space-time comes in.
Exactly. Space-time, a term actually introduced by his former professor Hermann Minkowski, isn't like saying space plus time.
Yeah.
It's a single, unified, four-dimensional structure. Think of it as one fabric, if you like.
Oh, 4 dimensions, okay.
And in this framework, events aren't just things that happen in space at a specific time. Events are points within space-time, defined by their location and their when, all together as one coordinate, sort of. And objects, from a tiny particle to a person, trace continuous paths through this space-time. These paths are called world lines.
World lines, like the history of an object.
Essentially, yes. It's the history of that object mapped out in this four-dimensional reality. Now, remember how we said clocks measure duration?
Yeah, not time, duration.
Right. Well, in the space-time framework, duration, what physicists often call proper time, is mathematically defined as the measure of length along an object's world line. And just like the distance you travel between two cities depends on the specific route you take.
The duration you experience depends on the specific path your word line takes through space-time.
You got it. Exactly.
Okay, so the analogy works. It's not just about the start and end points in space-time, but the specific journey you took through it that determines how much duration you experienced.
Precisely. And this geometric definition is why the famous twin paradox works.
Oh, the one where one twin travels fast and comes back younger.
That's the one. The twin who travels at high speed follows a different world line through space-time than the twin who stays put on Earth. Due to the geometry of space-time itself, how speed and gravity curve this fabric, the traveling twin's world line is effectively shorter in terms of proper time or duration. So they experience less duration, they age less when they eventually reunite. It's a consequence of the geometry.
Okay, that makes more sense explained that way. So if our personal experience of time passing is just us moving along our unique world line through this fixed space-time structure, and there's no universal now,
Yeah.
how does this framework change the way we think about the past, the present, and the future? Does it mean they all sort of exist simultaneously in some way?
It does profoundly challenge our intuitive sense of a single universal present moment.
Yep.
Absolutely. Because simultaneity is relative, what counts as the present, like a slice through space-time containing all events happening now, is different for observers moving relative to each other. There isn't one definitive privileged now for the entire universe.
Hmm.
So the implication is that from this space-time perspective, all events, past, present, and future from any given viewpoint can be seen as existing within the structure of space-time itself. Our subjective experience of moving forward from past to future isn't necessarily the universe itself flowing. It's us traversing our own individual world line through this potentially static four-dimensional landscape.
That is really mind-bending. If the past and future are potentially just there, part of this existing space-time structure, like the past events we remember, does this framework brush up against those huge fundamental questions of destiny or free will?
It absolutely does, and the source makes a fascinating connection here. It discusses the theoretical possibility of time travel scenarios that can emerge from some mathematical solutions in general relativity, like those found by the mathematician Kurt Gödel back in the day. These solutions describe spacetimes that could, in theory, allow for world lines that loop back on themselves, creating what are called nearly closed world lines.
Like time loops.
Sort of, yeah. And such loops obviously lead to paradoxes like the classic grandfather paradox, what happens if you travel back and prevent your own birth?
Right, the paradoxes.
So the expert brings up this idea of a principle of coherence. It suggests that even if such pass-through space-time were possible, events would have to unfold consistently. You couldn't, for instance, successfully make a choice in the past that violates the very fact that you exist in the future to make that choice.
Ah, so things would conspire against you changing the past.
In a way, yeah. This is where the analogy of the Oedipus myth comes in from the source. How actions taken specifically to avoid a foreseen outcome become the very cause of it. Destiny fulfilling itself through attempts to escape it.
Wow.
And according to the expert in the source, the possibility of these theoretical time travel scenarios is currently the only point in physics where this age-old question of free will versus destiny directly intersects with the known laws of nature.
It sounds like even having this conversation is difficult because our language itself, the words we use, are so deeply embedded in that old intuitive idea of time flowing universally.
That's a critical point the source highlights, definitely. We use words like time, simultaneous, now, past, future, chronology. And these terms carry all the baggage of our intuitive, sort of Newtonian understanding. When we're trying to discuss space-time reality, we really need to be more precise, using terms like duration or proper time to accurately describe what clocks measure and how events relate geometrically. It's a real challenge because our language and our fundamental intuition are kind of playing catch-up to what physics is telling us about reality.
Okay, let's try and unpack this a little then. We've taken a deep dive into why modern physics, grounded in really precise experimental evidence and Einstein's revolutionary insights, strongly suggests that universal time as we intuitively understand it, well, it simply doesn't exist.
Right. The key takeaways are probably clocks don't measure a universal time, they measure duration, which is the length of their unique journey or world line through space-time.
And that's not just theory.
No, not just theory. It's proven by incredibly precise atomic clock experiments. It's absolutely essential for technologies like GPS to function correctly, and it's leading to exciting new applications too. The universe seems fundamentally better described by this unified four-dimensional concept of space-time, where duration depends on your path, And within this framework, the idea of a single universal present or simultaneity is relative, which does suggest past and future events might exist within this structure in a way we don't usually think about.
So if we connect this to the bigger picture, it really shifts our perspective. We're not just passengers on some universal river of time. We're more like traversers of unique paths through a vast, maybe static-like, four-dimensional landscape. And as we discussed, it brings physics face-to-face with some really fundamental philosophical puzzles about free will and destiny, which raises an important question for you, the listener, and frankly, it's one that even the expert in our source material admits there's no definitive answer to yet. If events from the past and future potentially exist within the space-time structure, much like the past events we can remember, why is it that we only seem to experience moving forward along our world line? Why do we only remember yesterday but never tomorrow? What gives it that direction, that arrow?
Yeah, it remains a great mystery, one that physics alone hasn't fully resolved. Is the answer purely in physics, maybe something to do with entropy or thermodynamics? Or is it something deeper, perhaps to do with consciousness or something else entirely? We don't know for sure.
Well, if this deep dive has sparked your curiosity and you want to explore these ideas further, the astrophysicist we drew from, Mark Likez, has written books delving deeper into these concepts. I believe there are titles translated as Journey in Time and The Age of the Universe. They're great resources for anyone wanting to go further down this particular rabbit hole. Thanks so much for joining us on this fascinating deep dive.